after discuss the file systems, okay, then let's talking about the secondary storage systems. That means the disk, okay, or magnetic disk, or most of the current disk is a flash disk, okay, or other type of material, okay, the storages, okay. In the past, the magnetic disk is used as a typical secondary storage. Okay. The drives rotated at the ratio of the 60 to 200 runs per second. Okay, so the transfer rate is the rate at which data flow between drive and computers. So it highly depends on your rotation time. Okay, and the position time, random access time, okay, is the time to move disk on to desired cylinder. Okay, sometimes we call it seek time, and the time for desired sector to rotate under the disk head, okay, rotational latency. Okay, so the total disk access time will be transfer rate, seek time, and rotation latency. Okay, so the read-write head is not directly touched to the surface head. Okay, but if they touch, okay, contact with the disk surface, then the disk will be crushed. Okay, the surface touched will be. And disk can be removable. Okay, in the past, there's a removable disk. Okay, and disk drive attached to a computer usually by I/O buses. Okay, the typical I/O bus are these USB fiber channels, SCSI, and so on. Okay, and the host controller in computer use this bus system to talk to disk controller and so on. Okay, so that's the basic idea of this. Okay. And this is a typical magnetic disk. Okay, you have a lot of service. Okay, and you have an on, and this read-write head. Each service has a read-write head associated. Okay, and all the read-write head were bounded into on. Okay, and by using this on, and this on will be controlled. Okay. By a step motor, so they can move directly in the line, okay, in a straight line, and to move in to the track or move out. Okay, and this this platter or surface, each platter contain a lot of tracks. Okay, so track and sector. Okay. And this, for example, this is T track T. Okay, so all the and cylinder is this cylinder C. Okay, and sector is inside this track. Okay, a cylinder C means the track number is the, okay. So cylinder is the position of this. Okay, so cylinder group is several cycles, and they are continuous together. Okay, so disk usually is, and then when we start up a computer and initialize the disk will start to rotate until it's in a constant speed of this rotation. Okay, and then the disk head can move in to very not direct contact, but very close to the data. Okay, so in the right track. Okay, or cylinder. Okay, this one is the same cylinder, and this track number will be 1, 2, 3. Okay, and sector number inside the same tracks. Okay, and so on. Okay. The structure of the physical disk, okay, disk drive usually address in a large one-dimensional array of logical block numbers, okay, and both logical block is the smallest unit of data transfer. This one-dimensional array of blocks are mapped into sectors of the disk sequentially, okay. Sector 0 usually is the first sector of the first track on the outermost cylinder. Okay, so go here. Outermost cylinder is in this side, this one. Okay, and the first track, and this is the first service, first platter. Okay, and the first sector. Okay, okay, that's all. And maybe proceed in the order through the track. Then the rest of track in the cylinder, okay, and then through the rest of the cylinder from outermost to innermost. So okay, so something like this. Okay, so the first track in the cylinder, in the outermost cylinder, okay, and the sectors are once this one is all the sectors in this track are numbered, then move to the next track, okay, in the same cylinder, and then until the last tracks of it, and then go back to the next track, okay, the inner cylinder, okay, from out to in, okay, something like that, okay. And this usually attached to a computer in the following way, by either host attached the storage through I/O port, talking to I/O buses, okay? And these I/O buses, SCSI is very common. They used to attach, can up to 16 devices on one cable, okay? And SCSI initiator request operation and SCSI target perform task. Okay, that's it. And each target can have up to 8 disks. Okay, so overall is 8 disks plus times 16. So total disk number will be something like this: 148 disk, okay, can be attached to a single SCSI table. Okay. And the second one is the network attached storage, or sometimes called NAS. It's a storage made available over a LAN rather than a local path. Okay, that means that you may have a storage host. Okay, and this one is directly connect to a LAN instead of, so it's not attached to any computer but attached to a LAN. So all the computer in this LAN can communicate with this storage. Okay, but through the network, not buses, okay, not system bus. Okay. The last one, this idea of the network enabled storage host be further extend into a storage area network. Okay, that means you have a area network, local area network. All the nodes in this local area are storage nodes. Okay, and then this whole storage network attached to a network. Okay, so all they can support a more large space number of storages. Okay, let's see. The NAS is something like this. This LAN, you may have some NAS node and some computer node. We call it client nodes. Okay, the NFS and Windows CIFS are common protocol via this client computer, and then go to the NAS nodes to get the storage. Okay, through this remote procedural calls between host and storage. And in the current, right now, there's a iSCSI protocol, they use IP network to carry the SCSI protocol. It's also common. Okay, so if instead of using this NFS or SIP in RPC, some system, some NAS support iSCSI, so they can be attached to the computer through SCSI protocol to simulate by using networkers to emulate these SCSI buses. Okay. The storage area network usually is organized by this way. So the network will have a lot of storage. They connect to this storage network. It's a separate private, and then you have storage array and other type of storage, for example, disk tapes, and CDs, or data processing centers, or web content provider. Okay, so and some servers. And then we have a normal LAN or WAN. Computers connect to here. They did not directly communicate with this storage area network, but they go through this server host or this data center database server or web servers. Okay, instead go through these service applications to access the storages. Okay, so these are another way to organize this storage. Okay, so by using this way, this client hoster, they can share this storage through the applications, not directly use the storage from its own application. Okay. To schedule a disk access, okay, because operation support multi-process or concurrent process. So simultaneously may have several processes. They are waiting for same I/O devices, same file system. Okay, but they access different files or different disk blocks. Okay, simultaneously. Okay, so the file system is responsible to use this schedule this access. So the overall throughput over performance will be much in a good condition, is efficiently enough. Okay, so for disk drive, this means that you have a fast access time, okay, and high disk bandwidth. Okay, so access time we mentioned it before. For a disk block, it will contain seek time, rotation latency, and transfer time. Okay, but because transfer time usually is the size of the sector, so it usually is not schedulable, because once we format a disk into a block size is decided, then the transfer time is decided. It is corresponding to this rotation time and the block size. Okay, so the important factor is rotation latency and seek time. Okay, and seek time is the time for the disk head to move from current cylinder to another cylinder. Okay, because if the next required sector or block is not in the current cylinder, then you need to move this disk head around. Okay, rotation is the additional time waiting for the disk to rotate to the right desired sector. Okay, so in average, this rotation is half of the rotation time of a disk. Okay, so and this time is in general is much smaller than seek time. Okay, because the disk head, the movement of disk head usually is controlled by a step motor. Okay, it's a motor, and the motor is not electronic. It's an electronic motor, all right, but the physically it's a mechanism operation. So the disk head is a mechanism, so they physically move the disk head from one place to another by this motors. Okay, so that's the much slower than this rotation. Okay, latency. So seek time is the major factor of this exit time, disk exit time. So most of the disk schedule, the purpose or the objective of it is to minimize this seek time. And so seek time in general is equivalent or relative to the seek distance, the distance between the current and the new head position. Because remember, the disk head are moved by the step motors, and the distance, and the step motor usually move in constant speed. Okay, between the head, between the track. Okay, the movement time is depends on the distance. Okay, and the disk bandwidth, the total time of byte transfer divided by the total time between the first request for service and the completion of the last transfer. Okay, so that's a disk. But actually the only parameter, okay, we can control by the scheduler is the seek time, because rotation latency is fixed. Okay, because the disk is rotating in a constant speed. Okay, and the transfer time is fixed also, because it's high. It depends on the block size. Okay, so from the point of view of the scheduling, the only factor can be adjusted is the seek time. Okay. So the disk schedule algorithm we are talking here are all concerned about minimize the seek time. Okay, and several commonly used scheduling algorithms are following. Okay, and we will discuss these algorithms according to the following examples. Okay, for example, here we have a request sequence. Okay, and this sequence are serial numbers, and serial number in 0 to 101. Okay, from outermost to the innermost. Okay, and the request, because only seek time can be adjusted. Okay, there's almost scheduling algorithm, they only concern about seek time. So the sequence we only here we only record the seek time. Okay, the serial number, and they are serial number of 98, 183, and so on. Okay, and the column head position is in cylinder 53. Okay, and we have these following algorithms. First come first serve, that means the request, the service this request according to their arriving orders. Okay, assume the arriving order is something like this. Okay, is the queue, the order in the queue. And then we have a shortest seek time first. That means the position between the waiting, the current, and the waiting request. Like which one is the shortest distance? Then we serve that one first. Okay, send a request with the minimum seek time for the current head position. Okay. The next one is scan. Scan is very similar to elevator. Okay. Schedule the pending IO in the sequence of the current head moving direction. Okay, according to the direction. Okay, we scan. Okay, if it's moving from outermost to the inner, from 0 to 199, then you serve all the requests. The data, the head is moving in one direction until the end, and then they reverse the direction and move from the other end, move back. Okay, so when scanning moving in this direction, then all these close by sequence requests are served. Okay, according to this direction. Okay, when the head reaches the end, it reverses the moving direction. So it's like a elevator. So when you go up, maybe you go to the top floor, and then you go down, you go to the bottom floors. Okay, and all the floors they close by, all the requests they will service those passengers. And here it's similar. Okay, so it's an emulation of the operation of the elevators. So sometimes this can we call it also named as elevator. So named as elevator algorithm. Okay. And the Stein variation of the scan is Duke. Okay, that means when you move in from one direction, but you will not move to the top, to the end. You only move to as far as the last request in that particular direction. For example, you move from 0 to 1 to 9, from the out to in this direction. But the last request in this direction is in, for example, 14. Then you will not move to 0 because 90 is 183, for example. Okay, because there's no request after 183, so you reverse direction immediately when you find out there's no direction in that direction. Okay, so look is look ahead. Okay, you look the current direction. If no more requests in that direction, then you reverse. Okay, and then move to the other direction. Okay, until the last request in that direction. Okay, then the last one is C scan, is a circular scan. Okay, we schedule the pending I/O in the sequence of the head moving direction. Only service one direction. When the head reach the end, if first move the head back to the other end, and this first move without serve anything. So because this from one end to another, and without stop in the middle. Okay, so you can accelerate this head movement to the first. Okay, and then the other hand has a braking mechanism. So you move to there's a special brake mechanism. So they will stop in the other hand, and then you service. Use a normal speed to go from one end, the end to another, and then during this normal speed of movement, head movement, it will serve all the requests pending in that direction. Okay. So serve requests only in one direction. Okay, the other part is just a fast movement to go back to the end. Okay. The reason for this scan is that for scan and loop, you will find out that the cylinders, the request in the middle cylinders, they will service in two directions or in this one direction. Okay, they will get more service possibility because they move this direction in the middle. They will get served, and then when they return back or move the other direction, if there's a subsequent that comes in the middle, they will also get service. But in the two ends, most of the time they will only get one request from this direction. Okay, only one direction, and then they will get another. So C-scan will make all the services more. They have the more fair opportunity to get service because they go from this way, they will get service, and then the back movement will not provide any services. Okay, so everybody get the same opportunity to be served. Okay. So let's see first the difference. Okay, so Q is in this order 98, 183, and so okay, and the 0 is in the outermost. This is outermost the cylinder, and this is the innermost cylinder. Okay, so the current head position is 53, for example here. Okay, well, so for in first come first serve, we don't the direction is irrelevant. Okay, so we serve the one which has shortest distance. So in this is 65. Okay, so so we serve 65 first, and then 67. Okay, and then oh no, first come first serve. They serve according to this position in the queue. Okay, so 98 gets served, and then 183, and then 37, and then 112, 122, and then 14, followed by 112, 24, 65, and 67. Okay, so total 6 times will be the distance between this movement. It is 6 and 38. Okay, for shortest 6 times first. Okay, so starting from 53, the shortest one near this one to the 63 will be 53 will be 65, and then 67, and then 37, 14, and then 98, 122, 124, and 183. Okay, so you find now the total 6 time will be 320. Okay, yeah, it's much smaller than this first come first serve. Okay, for the scan, okay, if the head is in 53 and it's moving from 0 to 199, moving in this direction, okay, from 0 to 199, the direction, then 53, the next one will be 65, 67, 98, 122, 124, 183, and then 199, and then go back to the direction, go to 37 and 14. Okay, so total is 331. Okay, 331. It's very close to this shortest 6 time first 320. Okay, but this one is much simple because the algorithm is much simple. You did not calculate the distance of the current head and the next request. You just go through one direction and all the and then in this direction there's something there. You stop there and handle this request. And so, okay, so the algorithm is simple, but the performance is not too much less than this short 6 time first. And for the scan, okay, we go one direction to 199, and then time for the fast movement back to the 0 can be ignored. You just move very fast back to the 0, and then so 14 and 37. So the total time will be 183 plus this fast movement. Okay, and in general, this fast movement will be much less than the distance of this 199 to 0. Okay, this is 199. Okay, but the worst case will be what? If this is the same speed of this is 199, then it's 382. Okay, so the worst case is 382. But in general, this fast movement is much quicker than this normal speed movement. Okay, maybe say for example 10 times faster. Okay, if it's 10 times faster, then this will be 199 over 10 is 20. It will be around 20. So it will be 213. Okay, so that will be much faster than this short 6 times first. Okay, but if the speed is 5 times faster than the normal speed, then this one will be divided by 5. Okay, 200 divided by is 40. So even 5 times faster is good enough. 40 is 223. Okay, and if so say only 2 times faster, so this will be 100. It's 283. It's still faster than shortest 6 times first. Okay, so that's why scan is much prettier, and also the you can see that the probability to get served, the waiting time, okay, for the request in the middle will be same as the probability of waiting time in the both end. Okay, so it's much fair for all the requests. Okay, so this can get fairness and efficiency both. Okay, and the look is something like this. Okay, you look ahead. Okay? So when we serve the 183, we find out there's nothing there. Okay, in other end, so you immediately turn back. Okay, so the total seek time will be 299. Okay, but because it has the same disadvantage of this scan. Okay, the request in the middle has high possibility to get served. So their average waiting time is much smaller than the average waiting time in the both side or both end of these cylinders. Okay, so it's in some sense it's not fair enough. Okay, it's a simple problem as the scan. Okay? So most modern systems they use something similar to C-scan. Okay. The last topic in this overview, okay, principle OS principle, we will discuss this array structure. We mentioned that before. The array stands for redundant array of inexpensive, or independent disks. Okay. That means you just a collection of disks, and they are offshore. They are very cheap, but with proper control and put it together, you can get a high bandwidth and high redundancy and high reliability. Okay, so it contains multiple disk drive to provide reliability by storage redundancy. Okay, and also increase the mean time to failure. Okay. So the reliability will be highly increased. Okay. And there are 7 different levels of RAID, from RAID 0 to RAID 6. Okay. The RAID 0 just use disk striping to group disk into one storage unit, and by using striping, you get better performance. Okay, but without better reliability. Okay. And RAID 1 is mirroring or shadowing, a keep duplicate of each disk. And stripe, so middle, that means you a set of RAID you separate in 2 group, and every two disk has a middle disk. Okay, they contain identical data. Okay, so by using this mirroring, okay, or duplicate of two disks store the same information to improve the reliability. Okay, and more. There's a 2 combination of RAID 0 and RAID 1. Okay, we call it striped middles. That means RAID 1 plus 0. Okay, you middle in first and then stripe. Okay, so middle first and then stripe. So we call it striped middles, or middle stripe. Okay, that means you stripe first and then doing the middle. So it's a RAID 0 plus 1. They all provide high performance and high reliability in the same time. Okay, so middle only provide reliability. Striping provide better performance. Okay, and put them together, then you get good performance and good reliability. Okay, and RAID 4, 5, and 6 they use block interleaved parity. They use block, and then each block has a parity. A whole block have a parity. Okay, but the parity is using different kind of setup. Okay, so that's the block level parity. Okay, and RAID within a storage array can still fail if an array fails. So there's some automatic replication of data between arrays usually common. So okay, we can have 2 arrays. Okay, they duplicate each other. Okay, so one ray fail, another one automatically. Okay. And also some of the ray, they, besides this normal ray 0 to ray 6 upgrade, they also have some small number of hotspot disk. They are left there without unallocated, so they can automatically replace in the failed disk and review the content of failed disk from this hotspot. Okay, hotspot means the disk is running, but it's initialized and formatted already, but without any content. So once any disk fail, the reviewing of the failed disk will automatically take place in this hard space, hard standby. Okay, and then the operator or the will be notified, and then operator comes in to move out this repaired this failed disk. Okay, and then they may purchase a new disk and then put it into and then this newly acquired disk will become a new hotspot. An original hotspot will be, after review, they will automatically become part of the disk array. Okay, that's the very frequent mechanism or policy used. Okay. So let's see the detail of this. Ray 0 is no redundancy, but we using straight. That means you treat this 4 disks, for example, as one. So the first block is stored in here. Second block and third block, fourth block, and then strike and so on. So when you're doing the sequential access, the first 4 block can, because these are 4 independent disks, they have their own drive. Their first disk, first block will be get immediately. So the file, so the first 4 block of file will be striped into 4 disks. So whenever we try to get the sequential access of this file, the system will automatically get the first 4 block of this file, and because these 4 block, 4 disks are a parallel operation, so the response maybe can 4 times faster than single disk. And all the disk block of a file is stored in this single disk. Then you need to have full access to this disk. But here, you access every disk 1 block, and they simultaneously can be accessed. So using this striping can gain performance as fast as 4 times. Okay, of course, the 4 times is the upper bound. Okay, in general, it cannot get that, but can get very close to 4 times. Okay, another one use the middle. Let's say, for example, you have a 4 and then 4 as a middle. Okay. So every disk has is middle disk. Okay, so every time if this one crash, then the content of this one can immediately used to review this one. If we have a spare, okay, a hard standby in this here. So for example, this there's a 9 disk and this 8. We use this middle. Okay, so this one crash, and the content of this one can be used to copy to review this hard standby, and then this crash will be took out, and later you acquire a new disk and replace in here. So now this repaired disk will become hard standby. Okay, and so on. Okay, and put these two together, we have this ray 0 plus 1. Okay, that means we stripe middle after stripe. Okay, 0 plus 1 is middle striped. Okay, middle after stripe, middle striped. Okay, so this is middle striped. So we stripe and then after stripe with middle. So each group, disk 1, 2, 3, is a striping group. Okay, and then these two groups are middle. Okay, so A, B, C, D, E, F. The blocks are numbered like this way. So A, B, C, D, E. Okay, and the content of A is identical to this A. That's the 0 plus 1. Okay, striping, middle of stripe. Okay, so middle of the stripe. Yeah, right. Okay, middle after stripe. Okay, and this one is another step is 1 plus 0. 1 plus 0. Okay, it's stripe after middle. Stripe after. So first we group every 2 as a middle group. Here the group is a middle group, and then we use striping data into this 3 middle group. So A is in here, and then B, C, D, E, F is something like this. They all gain similar reliability and performance. Okay, because you have 2A and 2B. Okay, so any single disk of crash, for example, this one crash, we can review this one by enhance and put it into this striking group. Okay, about patient group into this middle group. Okay, it's all. And RAID 2 is the memory style error correcting code. Okay, so a block and every byte of the block. For example, is memory style error correcting code. So using the Harmon code, error correction. So any bit fail, we can automatically correct. And what's the error correcting code? We will discuss in the later topics. Okay, but here you just remember it's an error correcting code used as a parity. Okay. And their parity are stored. For example, and this is a bitwise parity. So okay, the blocks, corresponding blocks of these disks, they are the corresponding bitwise error correcting code are stored in here. Okay, so the 7 disks are working together simultaneously. Whenever you try to load a block, then you load 7 blocks of this into the memory. Okay, and then if any of this block, any bit has error, you can automatically recover from this redundant. Okay, and so there is a memory-based error correcting code. Most of the memory using similar mechanism, but here we just using this memory algorithm, management algorithm in physical memory in disk. Okay, and RAID 3 is the bit interleaved parity. Okay, so again it's a bit level parity. So there is 4 bits in the corresponding block. They create a parity bit. So it's only for error detection, not for this is for error correction. So we need to have more parity in here. We only have 1 parity enough to detect there's an error or not, but it cannot recover. Okay, it cannot recover. And RAID 4 is a block level, block interleaved parity. Okay, it's not bitwise. Okay, it's block level. Okay. And RAID 5, RAID 6, RAID 5 is also a block level interleaved distributed parity. So the parity is not corrected into one single disk, but they distribute this parity. So every disk has a portion of blocks that are used as parity blocks. But this parity block is not the parity of its own the disk block of this, but the parity of the others. For example, this portion of parity are the parity blocks for these 4 disks. Okay, and so on. So the parity and the data block associated with the parity block are separate. Okay, so but the mechanism is similar to this block interleave parity. Okay, but the only difference is they don't move, they don't collect this parity block into one single disk, but distribute. Okay, and according to their so the parity is always in different blocks. We of those related data blocks. Okay, and that one is P plus Q redundant. They use two different redundant. Okay, P and Q. You have two parities. So we can detect two different errors. Okay, but so they can cause more errors. Okay, you have two parity, independent parities, P and Q, and so on, and also it's distributed in some sense. Okay, and the ray 1 plus 0 versus ray 0 plus 1, they are both combination of this 1 plus 0. Okay, 1 plus 0 is the stripe of middle or stripe up. A better fault tolerance level. Okay, because it grouped the disk into pair of two or middles. Okay, so they do in the middle first and then stripe. Okay, so middle after stripe after middle. Okay, or stripe of middles. Okay, same. And so for 6 disks, there will be 3 groups. Okay, and within each group, data is middled and that's and block and so on. Okay, and across group, the data striped in some sense. And 0-1 is called a middle of stripes. Okay, so stripe first and then do in the middle. It group the disk into 2 middle groups for middle. Okay. And for 6 disks, we create 2 groups with 3 disks each. Okay. Within each group, data is striped, and block A is written to disk 1, disk 2, disk, and so on. And then across the group, they are mirrored. Okay, and this one has better fault tolerance. Okay, we try to figure out why this one has better than this one. Okay? Only compare to these two. Okay, just very similar, but a little bit different. Okay. Okay, so we finished this OS overview. Okay,